now let's take a closer look at the angular momentum of a planet as it goes around the sun, or any planet going around any star. So first of all, we define the angular momentum as simply being the cross product of the position vector and the momentum of the planet. And the momentum of the planet can be written as the product of the mass times its velocity. And of course, we're using the velocity vector there. Now, since the force between the planet and the sun is directed always along the position vector, and so therefore it is called a central force, there is no torque on the planet, which means if there's no torque on the planet, there cannot be any change in the angular momentum of the planet. So therefore we can write that the torque is equal to the cross product of the position vector and the central force, the gravitational force known as the Newton's gravitational force. And since they are 180 degrees apart, in other words, the position vector is pointing in one direction and the gravitational force is pointing in the exactly opposite direction, the angle between them is 180 degrees and the sine of 180 is 0. So therefore that cross product equals 0. So therefore there's no torque on the planet. And then if there's no torque on the planet, then the angular momentum of the planet has to be conserved. In other words, the torque can be written as the change with respect to time of the angular momentum, and therefore since the torque is 0, the change in the angular momentum must be 0, and therefore the orbit is confined to a plane. That's why the planets always stay within the same plane. Of course, since there's other forces involved in the solar system, there will be some slight variation to that, but if you ignore that, if you only consider the force between the star and the planet, you will find that the orbit will be confined to a plane. Then if we take the equation, the second law of Newton, as F equals ma, and then we realize that a can simply be written as a second derivative of the position vector, then you can see that the gravitational equation gmm over r cubed times the position vector is equal to the mass times the second derivative of the position vector. And then we're going to take a look at the solution of that differential equation in various forms, but you will see that the solution to this equation will match the laws of Kepler as we know them, the laws of motion of Kepler. So that's what's coming up. We're going to take a closer look at that differential equation and see what type of solutions we can get out of that. But at least now you see the relationship between the central force, the force of gravity. We can see that the torque caused by that force must be equal to 0. Therefore, there's no change to the angular momentum. It is conserved. Therefore, the orbit will be confined to a plane. And then we can define the gravitational force as being equal to ma. Of course, that will be the acceleration caused by that force. See, if there's an elliptical orbit, you can always see that the object will be, the acceleration will be along the direction of the gravitational force, but we'll take a closer look at that. We'll also take a look at how the change of the velocity will change in the orbit according to Kepler's laws, and we'll see how that all comes out of the solution of that differential equation. So stay tuned, and we'll show you some more of this. Okay.